पवित्रवतु ॐ चोदयेत्रे सूनृतानां चेतन्ति यज्ञं दधे सरस्वती।
Present is the key to the past is a philosophical statement. Most of us would have identified that when we look at our day-to-day lives, we look at the present and we take it as an indicator for the past or some references in the past. But in today's topic, we are going to talk about a scientific approach where we are using geology, a subject of earth science, and in the perspective of geology, we are going to understand the meaning of present is the key to the past. This statement is very quirky, but it is not a very common statement, but it was made by James Hutton, who was between 1726 to 1797. And according to him, what we see today can lead us to the past, that means tell us about what happened exactly in the ancient past. We also had another scientist, Charles Lyell, who spoke about uniformitarianism. That means there was a uniformity of the beds or the sediments that were deposited in a particular basin, and from that the different information that we are getting, that we are able to see today or collect information today in the field is because of several events that may have occurred in the past. So what is geology? Geo, that is earth, logos is logical study. Geology is also an offshoot of another subject which is in the arts perspective, that is geography. But geography studies the surface of the earth, whereas geology studies the subsurface of the earth. It is most words, if you notice, would be derived from Greek or Latin, but geology has been derived from a British origin. It is a noun, so we can use it in the capital letters or we can use it as small letters. The proper definition for geology would be then the science of the earth that investigates the earth's origin, structure, composition, the earth's materials, the earth's physical structure, the earth's features that are developed by various processes that act on it, and the history. So here when we say about history, we are talking about the geological history. That means historical geology is a record of the past events. Since our theme is the present is the key to the past, we therefore require information which is historical in nature and a record of that historical data. I have also attached the website addresses wherever I have taken the data from, so you could always refer to the same sites. So what is then geology? Why do we need to study geology? Who needs to study geology? How do you know that you should take up the subject of geology? I have put this slide because I assumed there would be students other than geology sitting in this classroom, and they may want to know what exactly the subject of geology is doing in a science faculty. So if you can check mark any of these and find out. If you are very curious about the surroundings and its environs that you live in, you feel challenged by occurrences of minerals, rocks, soils, oceans, groundwater and atmosphere. That means you feel how did they come there? How are they present here? Amazed that a subject can combine arts, commerce, engineering and sciences, which is what we will see subsequently, how all the subjects come in, all the faculties come into play. The use of sophisticated instruments and technology. Geology is a subject where you are actually touching or using directly or indirectly to measure some information which becomes a record. So every aspect of geology, when we are looking at minerals, the occurrence of minerals, rocks, soils, oceans, groundwater and atmosphere, each of them require a different type of an instrument that has to be used. So the instruments here are very sensitive and very sophisticated. So that itself becomes a separate field of study. And of course, you need to know that if you are happy to be outdoors and you like to travel a lot, then yes, this is for you. So geology can be then, in that case, if all the points are check marked, then that means geology is a subject which you could explore. Now, what is the importance of this subject? Why geology? So, we know that since we are going to look at the history of the earth and also the past record, the historical record that is contained in all these rocks, minerals and the earth materials, it is very clear, therefore, it becomes an investigative type of a method that has to be used to understand the subject of geology. So, geological studies through investigative methods will lead to the understanding of the geological studies through investigative methods, because we saw in the earlier slide that it is something to do with traveling, being outdoors, looking for, searching for. So, investigative methods which leads us to the origin and evolution of our planet. How did the planet originate? When did it originate? How did it originate? Processes that operate at and below the surface of the earth. The chemical and physical properties of the earth materials. Earth materials we already defined earlier. The structure of our mobile crust. We know that in the past, the continents were joined together. They have moved apart, and where we are now is after the movement has taken place, but still ancient records show that they are still drifting. So we would like to know more about that. To find, develop and conserve natural resources like forests, groundwater, things that cannot be replenished, and once gone it takes millions of years to generate. So they are natural resources. Our water supplies, and strive to keep them clear of pollutants because we are having all sorts of like industry that has developed, and materials that fall into the water because of the running streams that reach that particular water body and carries with it the pollutants from the industry. So we need to do that, we need to look into that. The history of life preserved in the rock record. Now, history of life preserved in the rock record is a very important statement where geologists are concerned. Now, how would life be preserved in a rock? So that is what we are going to see in our subsequent subsequent slides, and we'll try to show how the rock record gives us the evidences of life in the past. And the human adaptation to earthquakes, volcanoes, landslides and floods. Now, these are natural disasters. But how do humans adapt to these disasters? It is different in different places. It depends upon the preparedness of that particular locality to face these kind of natural disasters. So, by studying the past and present record of these events, we gain insight of how these processes work. This helps us predict the behavior of the earth. So, given the fact that earth materials are so many, like you have water, rocks, minerals, soils, you have atmosphere to deal with, groundwater. So, and pollution, we talked about pollutants also, and disaster. So, it is very obvious that the subject requires inputs from various other faculties or various other disciplines. So, an interdisciplinary subject, that is what geology is, and that can be proved. For example, the minerals which is one of the earth materials. We require chemistry to tell us more about it. How did it come to be there? So, geochemistry is the term, and most of these subdisciplines, once they join with geology, then they are again coined into a new term. So, you have geochemistry, which is again chemistry, study of chemistry of earth's materials where minerals, rocks are involved. Geophysics, what is happening in the subsurface. You need sophisticated instruments to find out to give you back some information. So, that is geophysics. Stratigraphy, strata, that is layer, graphy, that is writing. So, you are writing the information about the layers of the rocks. So, it is the study of such stratified rocks through the time, that means from today to the past. So, a stratigraphic record gives the chronological sequence of events. Chronological, that means time with respect to absolute time. Then you have paleontology, where you study fossilized plants and animals. Of course, now this plants and animals comes in biology. So, we are looking at the plants and animals which have been fossilized, and we study in paleontology with regard to their distribution in space and time. That means, like for example, on all the continents we have humans, on all the continents we have certain forests, on all the continents we have certain animals and plants. But there may be some continents we do not have a particular type of a life form. So, that also will be studied with respect to space and time. Therefore, this subject is closely related to biology. The only difference in biology and geology studying this aspect is they study the life when the animals are alive, whereas we study from the fossilized to the past. Mineralogy, the study of the natural inorganic substances, that is minerals. We have identified up to 3,600 minerals as of now, and they have been, but less than 50 are actually common constants of the rocks that you see around you. Geomorphology, this is where you have the study of physical processes, the action of water, action of glacier, action of wind on the earth's surface, which leads to different types of landform development. You can see how much of interdisciplinary aspect that the subject has. It continues. Petrology, study of rocks that deals with the origin, composition, structure and alteration. Structural geology, the study that deals with the form, arrangement and internal structure of the rocks. And economic geology, study of mining, coal and petroleum. Engineering geology, where civil engineering comes in. Most engineering colleges have the subject of geology in civil engineering. The application of education experience in geology and other geosciences will solve the geological problems which are posed by civil engineering structures. That means your dams, tunnels, bridges, etc. Now, the interesting part is the human use of materials has become so great that waste materials are influencing natural geological processes. So, as a result, a new discipline called environmental geology is starting to emerge. Now, what happens here is the word environmental is prefixed. So, you have a new subject and then you find that the environmental aspect is like with respect to air, soil and water, so then becomes environmental science and then geology takes the back seat. So, as a result of this kind of interaction, you get new subjects that come into that start emerging. So, now knowing the reason that you want to take geology and what exactly you are going to study in geology and the interdisciplinary nature of geology, what is the specialization that you can actually do? So, if you are specializing in studying of water, it is hydro. If you are an environmental geologist, if it is studying the landforms, geomorphologist. If it is past climate, it is paleo. If you want to study rocks, it is petrologist. Minerals only, mineralogist. Geophysics, that means if you are looking at understanding the subsurface in greater detail, then it is a geophysicist. Geodynamist and geochronologist, glaciologist, all these are the different fields where a geology student can specialize in. And then each of these specialized subjects, they have a separate job market. So, it is not that a person studying geology will be taken in any one of these which is shown as a specialized. You can see it just continues because it is an interdisciplinary subject. Structural geologists, stratigraphers, sedimentologists, paleontologists, marine geologists. I have already explained the meaning of these prefixes. So, you would know that a person studying sedimentology, that is sediments only, would be sedimentologist. Studying only the rock layers, stratigraphers, only the fossils, paleontologists, and those who are studying ocean, that is and continental shells are marine geologists. We have NIO, a separate apex body which takes care of the marine geologists. You see, you can go further. You want coal, petroleum, oil, you want economics to be done, you have an economic geologist. Engineering geologist, a geochemist. Much of our information has come from the chemistry. So, a geochemist, that is a geochemist, basically a chemistry person who has wandered into geology and found out the information. Planetary geologists, now we are expanding to space, that is planetary geologists. Volcanologists, we had a staff who was specializing in volcanoes only. The staff, she just wanted to be near a volcano. So, she is actually a volcanologist. She is a geologist, but specialization is volcanologist. So, now she is maybe in near some volcano in Mexico, because that is where she has gone right now to study more of volcanoes. Then you have seismologists who study about earthquakes, how they occur, when they occur, why they occur. Next. Right. So, having understood that, you can have like job prospects in different aspects of geology, because geology has that many branches and that many specializations. So, it is possible that we can choose our niche and take up that particular field. So, we come now to where is the earth, because we have been talking about the earth. So, you will see in our solar system, the earth is the third position, and with respect to the rest of the planets, it is very small in size, but it is very heavy. The first three planets, they are very heavy. The rest of them are lighter, but they are larger. Now, to get the complete picture of the earth, like you only know what earth looks as you walk down the streets or you visit some places. But what happens when you look at the earth holistically from outside from space? Then this is what you get from satellites. So, we have satellites which have been taking pictures continuously from past, that is from 1930s to present. So, we are able to see the first one which I am showing there is a colored one, it is a colored image of the earth. Second one is an infrared image of the earth, and how the information from the satellites is placed on top of the earth, and then we analyze it for global climatic changes, etc., or studying the weather phenomena, or studying the ocean surface, or the wind which is generated and how it moves over the ocean and the land surfaces. So even that can be understood by just placing the data on the globe. Now here you can see a network. Those are actually our latitude and longitude. It looks very simple, it is very humble, but that is the main base of all the calculations that are normally carried out in geology as well as in any other advanced study of geology, which has been shown earlier. So this latitude, you have your latitudes and you have your longitudes, and each of them are giving you a location in terms of degree, minutes and seconds. So even if you are looking at a particular activity that is going on, it is occurring between certain latitudes and between certain longitudes. So you know the extent by looking at that grid. Now in today's topic we have so many things to discuss, but instead of that I have just reduced it to just one small topic, which is the stratigraphy, where we are studying about the earth layers, layer by layer, and we are trying to unravel the past. What is in that layer, whether it is with respect to the earth materials like rocks, the soil, the minerals, the fossils. So you will see here, this is giving you in terms of percentage, how much percentage of time has been taken for a particular time period. Now for example, if I want to say where am I today, I am in the recent. Recent means as of now it is 0, or the number of hours on the clock. But if I go backwards in terms of days, months or years, I can go back to up to 4,500 million years. So what has happened to the earth from 4,500 million years to today? That is my question with respect to stratigraphy. That is what a stratigrapher would actually unravel. So what he has to do? So he needs to have some basic guidelines of how to go about understanding the present is the key to the past. So he needs to know certain things which will help him to get through. First of all, he needs to know what are the rock types. Then he needs to identify or classify that whatever he sees into different units, because every rock is not the same. To a layman the rock is a rock, but to a geologist the rock is not the same. We have to analyze the rock. So we can identify the rocks with respect to lithostratigraphic units, which is based on the properties of the rock bodies itself. Unconformity or bounded units, that means if you have a rock body, then is the next above it or below it together with it, or is it separated and something else has come in its place and not the same as the one above or below? So that is unconformity, there is a change or there is a break in that particular rock body. Then biostratigraphic units, again bio, that is fossil, so fossil content of the rocks. Magnetostratigraphic units. Now here what happens is every rock has a mineral called magnetite, or we say iron, right? So this iron gets polarized once in 11 million years, and it shifts or reverses the poles. So if you are able to identify in the past when did it reverse, then we know the time frame and we are able to identify the age of that particular rock based on just understanding the magnetostratigraphy. Then seismostratigraphic, where you are using the seismic records which have been obtained from the subsurface data that has been collected from sophisticated instruments. Then chronostratigraphic units, which are based on the units that is based on the time of formation of the rock bodies. So how do I put this? If I say a human being, the time he is born, it is 0. But when let us say the same human being grows through life, and say at the age of 70, his life is complete, he is dead. So 0 to 70 will be our time frame. So what happened between 0 to 1, 0 to 2, 0 to 3 or 0 to 5? So we can divide this 0 to 70 into separate units or individual units, or we can group them. So let us say in case of humans, we say 0 to 3, they are toddlers. Then 3 to, we say they are small, and then we call them as youth, and we call them as adults. So we have given a time frame for the humans between 0 to their lifespan. So the same thing happens in the case of the earth. We start with 0, whereas the earth actually originated, and from then to present, that means when we go backwards from recent to the time the earth originated, we get what is the chronostratigraphic units, where we have a time frame. So if I say 0 to 5 or 0 to 3, a child does this. So For me, in my stratigraphy, if I say from recent, if I go back, say 10 million years, then I will say what are the events that have occurred. From 10 million years, if I go backwards to another 10, that means from 0 to 20, then what are the events that have occurred. So we have to go backwards and then identify the different units based on the activities or events that occurred in that period of time. You have the chronostratigraphic units, which are again as the same as we discussed, and the geostratigraphic unit, the geochronological units, they lie within the chronostratigraphic units. That means if a child is, we are looking at the activities of the child from 0 to 3 years, there are so many other activities that go on between from 0 to 3. So each of those activities can be timed, and that is like what is, we talk about geochronologic. In the case of rocks, we identify any change in the rocks between that particular period of time. Within that time, if there have been any change, then we record that as separate geochronologic units. Then you come across a situation where you have incompleteness of the rock record. So you are not able to trace a complete record of a particular event or a rock that is having that particular information, and you are not able to trace it further. It stops at some point. So then that comes as a part of our stratigraphic, very important in our stratigraphy, as a break of information. So when did that information break? Did it occur only in one place, or has it occurred all over the globe? Because an event occurs all over the globe or in some parts of the globe. So when was that time frame? So that time frame where data is lost or data is not existing again becomes an important information that we have to use in stratigraphy. So this is a table that just shows how we identify what we just discussed, the principles, how we put them in different categories, and what we study under each of those categories. So lithostratigraphic, when we say, we talk about a huge rock unit which is as a group, and a smaller one as formation, smaller is member, and a very small one is simple bed. So we have just identified how we go about studying the different lithostratigraphic units. Same way unconformity bounded. Of course, here when there is a break between the deposition, or there is a between different lithostatic lithologies, then we say that there is an unconformity. There is no conformable behavior between the two. So we identify that as an unconformity and identify it as a change in that particular time period. Just as we saw in the previous slide, any information which is not there becomes important. Then biostratigraphic again. Now in biostratigraphic, so if you are finding a fossil here, plant or animal, or here, or here, or here, then it becomes very important. When you say bed, it becomes, when you are talking about range, in that small time frame, interval between the two events, or if a particular animal or plant thrived, then that particular zone would be identified. Throughout, that would happen throughout the globe. It will be universal occurrence. And assemblage again will be in a very, very smaller unit than your range, and abundance, where it is more in number. We identify such bodies of rocks where we are able to find plants and animals which are fossilized, and if we are able to identify that in one locality, we try to search for it in some other locality, and then we identify that those two localities happened at the same time. Then of course magnetostratigraphy, where you have the change in the polarity or polarity reversals, and you have chronostratigraphy and other things. Next. Just go back again. Now, when we are looking at how do we identify, like I said, a child we can identify as toddler or as child, like we give the time frame. So we have this is a time frame, this is a very huge, okay. We are having era which takes several million years, and period is within that era. In that several million years, these many million years, these things happened. So that is period which lies within the era. Epoch is within the period. In that period of time, a small event has occurred. That is a very small, brief event. So we call it as epoch. Age. So what is the age of that event? When did it happen? What is the duration of the era? What is the time frame of the period in that duration of the era? And what is the time frame of the epoch or of that particular event in that time frame of the period which occurred in that particular era. So for example, if we are looking at this the disasters that are taking place. It is taking place now in recent. It is taking place in recent. What is the duration? 3 days, 10 days, 15 days. But has it occurred all over the world? No, it is only localized in some places. But some events trigger off elsewhere a similar disaster, but it may not be the same type, it may be different type. So in that period of time, we are able to say that there has been these many events. So we can identify the events, their duration, and in which period they occurred, recent, and which era. We are talking about quaternary. That means we'll go to the next one. Next one. Okay, now this is a little bit, like it's an image, so you will find it difficult to read it from the back. Now, what is happening here is this is the table that actually tells you. It tells you about exactly what we did there. You have the era, you have the period, and you have the epoch and the age, and here we tell what has happened during that period of time. So you will see that this one is very large. So this is very large. That means it's a huge long period of time. But within that, so many divisions are there. So in each division, there are again so many subdivisions. Under each subdivision, there is a duration of time, and in each duration of time, something has happened. And we have, as geologists, to go to those localities where these things have occurred and then identify and write down all the characteristics of that occurrence or that event, because that becomes a record for us, a geological record. Now, this is actually the life forms. So, in geology, we say that if you say 4,500 million years ago, there was no life. There was only upheavals, and because the earth was forming and things like that. So, we are not having life. But life started after some period of time, and we call that as the Cambrian. We have the Paleozoic period, Paleozoic era, where you have the Cambrian period and 6 more divisions which are shown here, and in each division we have a different type of life. So for example, we have insects in a particular period of time, we have fishes in a particular period of time, dinosaurs in a particular period of time. When I say dinosaurs, fishes, they are all life forms which developed from a particular period of time. Either they continued to the present, or they stopped in between, or they only were present in a particular small time period. So such occurrences where a particular life form, whether it's a plant or animal, occurs in a small such period of time, they become very important as they become indexed to the time. So if you find such a fossil, plant or animal, in any other sediment anywhere else, then you immediately identify the time period and you say that this particular sediment we are standing on or we are working with is of that particular time period. So we are able to then chronologically put the sequence of the earth materials in this particular time scale. We call it as the geological time scale. Next. Yes, so when we are looking at the geological time scale, we have to always keep in mind that we are looking at the entire globe also for that particular time period. For example, late Cretaceous is a time period. Now this, if I have to put it in absolute time, it is 60 million years ago. So what happened 60 million years ago? The Deccan traps, that means the magma that has come out at that particular period, just late Cretaceous, and just after that is known as early Eocene. These are the names given to that time period. So during that 60 million years ago, we had the magma that came out and covered all of Maharashtra. It also occurred in some parts of the world. So we have to identify whether that magma which erupted had the same composition and the material is the same of the same type that erupted all over, or was it different in composition. But most importantly, in that time period, we come to know the distribution of that particular Deccan traps. So in India, we have Maharashtra, where the entire Maharashtra is covered by Deccan traps. Only some parts of it has been left uncovered. So therefore, geologically for us, that some parts which are left uncovered is important, because 60 million years ago we can see it is Deccan traps, but what was not covered is not Deccan traps, so that is older. So we are able to go to those areas and collect the characteristics of earlier data, that means earlier sediments which are lying below the Deccan traps. Next. So what does the geologist do? Now he knows that he has to follow a time scale. He knows that his aim is to identify the materials, earth materials, and place them somewhere in the time scale accurately, and for that he has to take the help of fossils or some structures or something that can or some event that may have occurred in that area which may relate to the standard time scale. So when the geologist first goes to the field, he just does an exploration, he just reconnaissance. That means he just goes there and has an overview, like what am I going to see here, what am I going to get here. He takes samples from there, comes back to the department or his institution, takes thin sections, like we take thin sections, the rocks, can be cut into small pieces and ground, and then one of the sides of the rock pieces could be like polished, and then we can put it under the microscope and see the arrangement of the minerals, and from that we can identify the rock type or the rock, or if any structures. Like for example, if he takes a sample and does a thin section of that sample, of that rock sample, and if he finds water in it, that is fluids are present. So that means it is a very it is a ancient historical record that he can then bring out and show that that particular area belongs to that particular time frame. Sometimes he cannot see samples just the way he is in the standing on the rock and seeing. He may have to do some subsurface study. So for that he may use instruments, sophisticated instruments like you have a driller, that drills a hole into the subsurface and brings out a cylindrical core which is wet, and that is brought out in such a way that it is not disturbed, and the bottom portion is kept the way it is and the top portion is kept exactly intact, and the whole thing is kept on the table in such a manner that the sequence of the materials, earth materials from the base to the top is it is kept, the integrity is maintained of that particular law. We call it as a core sample of that particular core. So this kind of activity is normally done when you are doing for coal, petroleum or any ore minerals that you may want to search under the subsurface. Whereas something like that is done for, like I said, Deccan Trapes. I can go to Mahabaleshwar or Matharan and I can just get some samples just by standing on those rocks, because everything else is depth, all of them are of the same composition. Sometimes what happens is you may trace that, supposing this particular white rock is, you want to trace it, you want to study it, and you are following all its path. Somewhere down the way you may find that there are gaps, like there may be a stream or there may be a road or there may be some kind of obstacle which does not allow you to take a complete record in one sequence. So then what you do is you have to, you normally go with a companion, so you measure the breaks that you find, then you come back to the other side and then you continue with your study of that particular rock or any matter that you would have been doing studying on the field. Now this is something like we actually go up close to the rock body, and you can see like they are all layers. This is like a bed, each is a bed. So we can look at these rock bodies and we will find that there is a dark material in between. They are sediments. See, what happens is when rocks are formed, there is a period of time that the action of water, wind and glaciers, if it is a glaciated region, they continuously act upon the rock surfaces, they remove it, erode it, sediments are formed, then after some time the sediments are deposited, then they get again hardened because of the heat, etc. And then you have a new type of a rock body that may be, or magma that may be again erupting, and you have a new rock body that may be forming on the sediments. So these sediments, they normally will have vegetation. If you go to Matharan or Mahabaleshwar, you will actually, when you are passing that Panvel road, you will find the rocks, they are grey in color, then you have grass, vegetation, then you have again grey in color, again you have vegetation. So there you can make out, actually count the number of times the magma has come out, because there was a period of quietness when there was no magma coming out, only deposition and erosion, and therefore the sediments were formed. Next. Right. So when we go to the field, we do not understand, when we look at the rock bodies and they are like in situ, like as they are, we are observing it, we do not know exactly what has happened to that particular rock body. So what the geologists do is they first try to recreate what is on the surface and then what could be in the subsurface. So for example, in this case, this top part, it appears like there are green lines which are parallel, then you have a brown, again green, and again you have a yellow and again a green. That means this surface is appearing flat when you go to the field, but it may not actually be flat. In the subsurface, what you have is a body of rock which was horizontal. That means they were all one upon the other, just as we saw in the previous slide. They were just one upon the other, and because of stresses that was released from the subsurface, those soft beds, they started to rise, and with increase in stress, they continue to rise until they start to fold. So originally they were horizontal. So 1, 2, 3, these 3 lines would be like green, yellow and pink, but they were horizontal. But because of the stress, they have been uplifted and they are folded. So this, what we do here is, we identify whether there is any geometry in this, like in this kind of a, you can say formation. So we find that there is a geometry that we can identify, an axial plane, and we get into the geometrical understanding of the formation of that rock, and we identify that they are actually a kind of a structure. The rock was not like this, it was happened because of some stress and strain that acted upon it. So you are having some kind of a structure. So there are many structures then in that case which we identify in the field. If that stress continued to rise, then this entire bed will become horizontal, and after some time this entire bed can go reverse. So if it becomes horizontal, we call it as recumbent. That means in the sleeping position or horizontal position. But this whole thing can turn. So we then call it as overthrust, or we can also call it as overthrust because it has again gone reversed, or overturned. We can also call it as overturned. So here what happens is we then start to identify. So what are these? What is this? And how we identify or classify? Do we find a similar one elsewhere, or is this dashed line vertical, or is it also inclined? So we then find that in some cases we have such structures actually occurring in the nature which are more or less vertical. So we find we are able to classify these folds. We call them as folds. We give them the name of folds because they appear to be folded. So these folds can then be classified based on their axial planes and the axis that is passing through those crests, and we name them as anticline because the angles are they are not symmetry. They are they are symmetry, but the angles are not the same. So they are against each other. But in the case of syncline, that means in this case, you will have the angles to be the same. Next, we have another kind of a situation in the field where you will find that you are standing on a a normal flat surface, but you do not know that flat surface you are standing on is actually something which has gone up and down, in the sense faulted in the sense, like you may have this to be in the same line, but if this thing goes down, then, and it goes down along a particular plane, that is the fault plane, this is the fault plane, then this is known as the hanging wall because it is hanging on top of that plane along which it slid, and this was the original rock which nothing happened to it. So these arrows are important for us. How? We come to know therefore which rock has gone down and which has been stable. Sometimes nature plays a trick. This goes up and then we call it as a reverse fault. So you can have both situations in the field, but it is up to us to identify how we know which one is the reverse fault or the normal fault. So in the normal fault, the fault plane will carry the hanging wall, whereas in the reverse fault also, but it will be in the opposite direction. But this will never move. Yeah. So this is like, now again, everything that we draw as a line diagram, we convert into a block diagram to get the complete view of the study area. Why? Because this is an area of study or reconnaissance where we actually do the field work. We may want to drill a hole, or we may want to dig the surface and study the subsurface. So we need to have a block diagram in 3D. So this block diagram tells us exactly how the situation would have been had that area undergone faulting. Sometimes what happens is, this is the beach sand, this is a sea, this is the land. Now you have the beach sand, which we are familiar with it, but you do not know that as you are walking up down the beach, most of us walk across the beach and to the water, you do not know when you may go into deeper zones. So when we do this field work or reconnaissance or drilling, we get samples of various from various points from the surface of that water. We drill and get the core. So we come to know like what bed is where. Now for example, you will see that this has a different pattern, this is different, this is different, this is different. So this is, again in geology we have these patterns are fixed, we cannot change it to our liking. So it's internationally standard. So when you put dots, it automatically means beach sand. When you put something like this, it is a carbonate or a limestone. So then this is again something like clay, very fine material. And again this is something like a silt. That means you have sizes of that material varying. It is not more than, when you say silt, it is, you can say, like sand is for example 2 millimeters and silt will be slightly more, okay, so slightly less than the sand, and clay will be slightly less than the silt. And of course, in the case of limestone, it is a ooze. So now here we have a situation where you have the beach sand, you have this line which indicates the water line. So you do not know what exactly is in the subsurface because you can only see the water. So when you walk across the sand into the water, you do not know how deep you have to go. But when we take sections of these subsurface, of course, when I say subsection, when we take core samples of these subsurface materials, that means we are in a boat or a ship, and that instrument, the sophisticated instrument is there in that particular boat or ship, and we take the samples, the drilled samples. So these samples will then indicate to us what are the types of beds that are present. So you will see in section A, you will have limestone, you will have clay, you will have silt and sand. All these are present. But when you go to the next one, a little bit of limestone and rest of the things. But here limestone is missing. And here, supposing we were to take, you would miss even the clay. So this kind of a situation is very important for the geologists to know what exactly in the subsurface. So drill samples are taken at A, B and C, and we are able to identify the beds that are occurring. Now normally what happens is, had these beds been horizontal, then this would be at the bottom, then you are at the next and the next. So you would have them in a particular bounded. But here you will find that you are not getting the bound. So you will be only finding that there is an increase in the beds vertically in farther off, but a decrease in the beds when near shore. So, but laterally if you see, they are actually all there. So that is very important, and that leads to a law by Walter, who says that you will be finding this kind of a situation. So don't assume that there are only just 2 beds, there may be more, and the vertical will be increasing, vertical changes, so lateral has to be also changing, or it should be showing us the change. Next. Now we come to a situation where you have rivers which are transporting sediments and dropping into the ocean, because that is the resting place of the rivers. So when it does that, the sediments which are heavier normally go into the sea and fall into the sea, but as they fall, they sort out between themselves, and you will find the coarser ones are near the land and very, very fine ones are at the bottom of the ocean. So that is what we are able to see here: sandstone, shale and limestone. So these are the different materials that are being deposited. So this is your beach, this is normally your beach, but then these are the different sediments at the bottom of the ocean. Now next, what happens if the high tide of the water is continuously encroaching on the land? Then the sandstone, the sand particles which were near the land, they start sliding off into the sea, and the materials, actually it becomes a reverse, in the sense it starts going down and the sand goes to the bottom. But when you have a low tide where the water continuously recedes, then here what happens is you have the other way around. So you will have the limestone coming up and the sand going down. In the other case, the sand was on the top and the limestone was at the bottom. But the sand continues to move down. When the high tide is there, the sand goes up, and then regression time it comes down. So when it will start moving in the go to the previous, it will start moving towards the ocean bottom. And that's what we call as marine transgression, that is during high tide, and marine regression, which is during low tide. Next. Okay. Now for any study area, what a stratigrapher would do, he would study each and every layer which is present in his locality, and he would name them correctly in the proper sequence. He would put a demarcating line which indicates the thickness of that particular material or that rock type. So it's very important that we have the original beds or the sequence of beds of that study area before we make any interpretation from the fieldwork that we have carried out. So we will find that when we are doing our interpretation, we find that some beds are missing. So we have limestone here, we have limestone here, but we have the grey something, and we have the grey shale here, but we don't have the bed here. And we have the sandstone here, we have the sandstone there, but we don't have some of the beds which are present there. So how do you correlate? So when we do correlation, we have to see the bed above that and the bed below that. If they match along with the lithology, that means the composition, the structure of the materials, plus if any life forms were there, if they are also present and the same are present, then we are putting a one-to-one correlation for that particular bed. So we call this as a stratigraphic correlation. It's a very tedious process because every part of the earth's surface has to be stratigraphically correlated with one another, so that it is able to fall within the time scale of that has been identified, like in case of geology, or in the Indian, whether it's for a country or it's for the world. So we have like Indian standard, Indian time scale, or you have the international time scale, or you simply have the geological time scale. Next. So you have different types of life forms which existed in the past. So when you see the arrow at the top, that is today, that is recent, that means they exist till today. But here the arrow says that it existed from then to today. So if you find this particular fossil anywhere in any of the beds, then that means you can identify what age that particular bed would be. So same way, there is a fossil there which is occurring only for a small time period. So it did not occur again after that, which means that becomes a very important index fossil. So it indexes the time frame from the past to that particular time frame till when it survived, or before it became extinct. So we have different index fossils which we use to identify, if they are present in the bed, to identify the time frame of that particular strata, and then we give the absolute age to that particular strata. So that is given the age because that particular fossils were found there. Next. So this is called correlation. So this is your natural environment. You take sections and then you see that you get so much of information here but no information here. But then when you are correlating it, you are able to identify those beds based on the thicknesses and their composition, structure, characteristics, and then you correlate that this bed and this bed are of that section, that is here, here and here. So you are able to identify and then correlate the strata. Now why this is important? It is very straightforward, but why is it important? Because you will see that there is a kind of a structure there, and here you find that the beds have thinned out, whereas here it is quite large and the thicknesses are far more. So it is important that we take sections across, drill the hole, take the core samples and then bring out the correlation. So this is one way of correlating beds which have undergone some kind of a structural deformation. Next. So this is finally what we do after all this hard work. We have a table that we have to prepare, and in that table we put down all the information that we have collected. So it's a very rigorous table. We cannot make a mistake in this table because the table will be referred to by many other researchers who want to do a similar type of work in that same area. So when they want to work in the same area, they will always ask for the stratigraphic time scale or stratigraphy of that particular area and the geological time scale, and see that in that time scale what sediments are present in that area. And if a person has not ventured further, then the new researcher can take up additional work in that same area, or he can look for new beds or something like that, something new. There is always something to learn in the field. So you will notice here we have the different like era. Here they have written the word as age, but actually the word that is commonly used is era, because that is the maximum time frame that is given to the next column, which tells us about the beds in that period of time. So how many periods were there? For example, if I take the first one, 1, 2, 3, 4 periods were there. So if I take that 4 periods, that each period is having a typical kind of a lithology or a rock type which is named, given that local name. So we give names like supposing if you find calcium carbonate, so we will say calcium carbonate, the name of the lithology. So they have given that and the name of the place or the locality from where we first located. In stratigraphy, one of the rules is that if I go to the field and I locate, say, a fossil of a frog somewhere in Malabar Hill, if I find a fossil of a frog in Malabar Hill, my next step is to identify if anybody else has identified a similar kind of a fossil anywhere else in any other part of the world. If there is nobody who has reported, then that locality takes the name of that particular fossil, of that particular formation or that bed, and in the information we will mention that the frog fossil was found in this particular bed, but that name of that particular locality will be the standard. So that means globally elsewhere, if somebody else finds that fossil, they would give the name of the first name that was the first local name that was assigned to it. So in this particular formation, we give the names of the locality, which can be Indian or it can be like from rest of the world, and then we actually draw sketches of what we saw in that field and which is related to that. If we feel that some beds are not continuing, then we put a curly line which indicates that there is a break, there is no continuity. So that break which we saw earlier, that's the break that we are talking about, which is important, and then later on somebody can do research and take it up and add to it or delete it, whatever, but then update it. That's what we say. So today students who are learning geology, they cannot study the stratigraphy of Mumbai or of India as it was when I studied, say 25 years back. They have to study the updated versions. Many of the beds may have gone because of earthquakes, and many of the beds may have been washed away because of the floods, so they no longer exist. So the whole thing can be washed off. It's no longer existing. So therefore, the students of geology of today can only refer to the books which we studied as the base to know what was there, and then in today's stratigraphy, they have to learn and update themselves with the recent finds of the researchers and who have updated this stratigraphic table. So in this case, we are showing for salt range, okay, and how the entire data has been sequentially maintained and the record has been shown. So anybody who wants to do and cross check, they can go to that particular locality, identify from the map where it is, then go to that particular study area, study that lithology, and then say, okay, I have understood now this part of the stratigraph. So something like that can be done. So we take students for geological field works essentially to do something like this. So when we take them to field, we tell them, look, this is Deccan Traps. So when we say Deccan Traps, we say it is somewhere in the late Cretaceous Eocene. So somewhere we put it here. Then they have to know what is below that and what is above that. They also have to know that which are the areas which are having that particular Deccan Traps, which are the areas that are having in India or in Maharashtra. And they must also know whether the Deccan Traps are having the same chemical composition throughout, wherever they have been formed. And they find that in Bombay itself, from Uttan right up to Kolaba, the different shades of magma is seen. The magma is not the same. Even Canary Hills you don't have, you have volcanic tuffs, which are fine sediments. So that kind of information can be then added, and students can go to the field to verify or validate that information, or they can always add to it if they find something else. So that's it.